So while we've been having a lot of fun learning about change of variables, I would like to go over one more example, but before we do that, I kind of need to bring up a couple technicalities because since this is an advanced math course, there are some advanced theorems and rules that come along, and in this, next week is when we really start kicking this class into high gear and things kind of get a little more technical. So I figured now is good a time as any to start introducing a little bit of technicality into this class. And you're like, Dylan, this class is already technical. Well, what I mean to say is that, all of this stuff, all of this transformation business, okay, this change of variable business, all this transformation stuff with the Jacobian, and basically making our lives easier to solve things only works, okay? Only works if the following things hold true. So the first thing is that our transformation T, which is, so T would be something like x is equal to r cosine theta, y is equal to r sine theta. So T is a C1 transformation. T is a C1 transformation from UV to XY. So what this means, what this C1 thing right here means, it seems a little scary. All this means is that all first derivatives are continuous. That's all. That's all it means. Okay. So very important, but like r cosine theta, r sine theta, you take the derivative with respect to r, take the derivative with respect to theta. We always get functions that are continuous everywhere, so that works really nicely. The second requirement is that the Jacobian is non-zero. Okay, is non-zero. Now this should make the most amount of sense. Because if your distortion factor is a zero, right, it basically says that you somehow shrunk and collapsed an entire area into nothingness, and that is just kind of ridiculous. So we need our Jacobian, our kind of distortion factor, to actually be equal to something. Let's see, what else? So the function that we're integrating, we are integrating. So when we set up our double integral or triple integral or whatever, is continuous on the region of integration R in the xy plane, or xyz, whichever one, on the region R in the xy, or xyz. What do I say? On the region in xy or coordinates. Okay, so that's important. So yeah, this business here with the transformation still needs to hold true if we're doing, like, say, spherical coordinates, where our transformation is a 3D transformation, goes from one 3D region to another 3D region. And the last but not least is that our transformation T is one-to-one, except perhaps, right? Perhaps on the boundary of S, which exists in our UV land. Okay, so basically what this means is that we're not adding we're not adding too many points or taking away too many points when we're going back and forth between each area, right? That every point comes from somewhere else. So if you forget what one-to-one means, you can just bust open your pre-calculus textbook or Google what does it mean for a function to be one-to-one. Just check that out. So these are the technicalities that exist behind the scenes. And if you've ever thought about getting a degree in mathematics or maybe some higher level engineering or STEM field or something like that, a lot of higher level mathematics is actually focused on exploring these kind of fundamental theorems that basically allow math to work, right? There's a lot of math that we use that we just kind of use and say, oh yeah, it's always going to work. But, clearly there's problems that we run into, like dividing by zero, functions not being continuous, right? There's these like little kind of exceptions that we always kind of have to be worried about. So in mathematics, a lot of what you study, when you go higher is, what are the exceptions? Where do we need to be worried about? What are the functions that we can actually do this with? Because when we think of functions, we think of really simple things like x squared and cosine of x, but there's all sorts of functions that exist that we can define that maybe don't follow these rules exactly. So while it's fun and fine and dandy to use change of variables for functions we're very familiar with, higher level math examines, well, why do these conditions hold? Why do they have to hold? What goes wrong? Things like that. So if that's interesting to you, we can talk about it. You can just email me. But these are the technicalities that I wanted to cover. I wanted to do one more example that's in the book of doing change of variables to really drive in the point of how to do it. And it's not really a complicated one, but here's what it is. So it wants us to evaluate the double integral of e to the x plus y divided by x minus y dA over R, where R is the trapezoidal region, that is, that has vertices of 1, 0, 2, 0, 0, negative 2, and 0, negative 1. Okay. Now let's kind of sketch this and kind of figure out what the heck it is that we're being asked to do. So here is my x and y coordinates. And let's see, so 1, 0 is here, 2, 0 is here. Oh, let's make this 1, 0, 2, 0, 0, negative 2. Maybe it's down here, and 0, negative 1. It's right there. Okay, so our region of integration is this thing right here. Okay, that's our region of integration R. Now let's maybe talk about why we might want to use a change of variable here. Okay, so why use a change of variable? Because this region doesn't appear to be very complicated, and it really isn't, right? We could cut this into some pieces. Maybe we cut this region into 2 pieces and do an integral where the x bounds go from 0 to 1 and from 1 to 2, and then the y bounds go between whatever those lines are, right? And we could do this. The problem actually here isn't with coming up with the bounds. It's actually, how the heck do we integrate e to the x plus y divided by x minus y? Like, how do we integrate that, right? Like if we do the integral, or double integral of e to the x plus y divided by x minus y dx dy, let's say we set this up. How do you do this? Okay, do you do u substitutions? Do we do trig substitutions? Is it just e to something, right? Like what do we do, right? We can't do a u substitution, right? I can't say u is equal to x minus y because I don't have x minus y on the top. I got x plus y, very different, right? I can't just do a u substitution. It's not going to work. So what do we do? And you're like, well, I thought the whole point of this is that we're given a transformation, right? Isn't the point that we're given a transformation that takes us from some nice region in U and V land and takes us this way via some transformation where we say, like, x is equal to something and y is equal to something? And I say, yeah, you're right. Here we're not given that. This is an example, one of very few, that we come up with the transformation ourselves. Now, I would like to preface this and say this problem has been picked because it happens to work out very nicely, but largely speaking, there are entire classes devoted to, coming up with good transformations that make something like this solvable. Because, once I show you the answer, right? It's like once I tell you to use polar coordinates, all of a sudden integrating circles is easy. But if you didn't know to use polar coordinates, you would be stuck doing integrals that were just, quite frankly, absolutely god-awful to do forever and ever and ever. So there's a huge branch from mathematics focused on coming up with transformations that allow us to do difficult integration much easier. And so here, it turns out that an idea is to create our own transformation, And what am I going to do? The book does it, and I'm just going to do it, and this isn't meant for you to be an expert at saying, oh yeah, clearly, right? All this is just saying, look, this is a tool, and this is an example of how it can be applied. I'm going to create the transformation u equals x plus y, and v is equal to x minus y, okay? Now, why on earth would I do that? The reason why I would do this is because this basically turns my double integral into e to the u over v, dA with some Jacobian thing here, right? With some Jacobian in there. But ignoring the Jacobian just for a second, integrating, let's say if we were doing du dv, integrating this would be a piece of cake. Why is it a piece of cake? Because if I'm doing the integral of e to the, I'm going to write it like this, 1 over v times u du, if this is my integral, I get to treat 1 over v like a constant. And what's the antiderivative of e raised to a constant? Well, this one's going to be just v times e to the 1 over vu, right? And that's the antiderivative. Like, we're done. You can verify this if you want. Take the derivative of this. We're going to end up back here. So all of a sudden, doing the integration here, if we make this substitution, ends up being really, really convenient. And so we're just out of the blue creating a transformation. Now, I want to point something out, that this transformation is technically not the original transformation. This is the inverse transformation. What we have just come up with is the inverse transformation. It takes points from x and y. Oops, you're probably wondering why that's a v. That should definitely be an x. It takes points from x and y, and it assigns to them u's and v's, right? So it says you pick a point in this trapezoid, and it has some value, maybe 1, negative 1.5, and I can tell you where to send this point in my u and v land, right? That's what this does. This is an inverse transformation, okay? And so all the rules of what we've been doing haven't used an inverse transformation. We've been using just the regular transformation going from u to v. So at this point, we got a couple things to think about, okay? So one thing to think about is we need some, transformation. X is equal to g in terms of u and v. We need to put x and y in terms of u and v. That's like the first thing that we're going to need to do. The second thing we need to do is to figure out what this region looks like. This region looks like in my UV land. Okay, here's UV land. Why do I need that? Well, because even though making this substitution turns out to make this integral like actually solvable and doable, it could turn out to be that it transforms this region into something like completely just god awful that it could just look like this and just be terrible to integrate in and of itself. So we're hoping that doesn't happen, and surprise, it doesn't actually happen. So the first thing that we need to do is to figure out what this region looks like. And so what we're going to do is we're going to use this inverse transformation. And I know I put this as number 1. I'm going to put it off on hold for a sec because it's actually pretty easy to do. And I'm going to use the same tactic that I used in the last video because the same rules apply. What I'm going to do is I'm going to just call this part here, like, I guess I'm going to call it R1. And I'm going to call the next chunk over here going this direction R2. Maybe I'll call this one D2. Just kidding. That's a Star Wars joke. Then I call that one R3. And let's call the last one here R4. Okay. And maybe I should label some points here. So this was the point 0, -2. There's a point 0, -1. This is the point 1, 0. And this is the point 2, 0. Okay. So what I'm going to do is I'm going to write down R1. And the goal is to figure out what becomes of R1 if we use this inverse transformation to go from x, y into u and v. Okay, what becomes of it? Well, R1 happens to be the line y is equal to, well, it's actually just equal to x minus 2. Now, how did I come up with that? Because I'm a mathematical genius, because it's a straight line, and I know how to come up with the equation of a line going through 2 points, easy peasy, okay? So that's the line y equals x minus 2, where x goes from 0 to 2. And so we're going to use a very similar process where we're going to take a look at our transformation and ask ourselves, if that's the case, what happens to our, what does u equal and what does v equal? Well, in the case of u, we have x plus y, but y is equal to x minus 2 on this line. So this is x plus x minus 2. And v becomes x minus 2. So u is equal to 2x minus 2. And v is equal to just 2. Okay, so what does this tell us? This tells us that R1 maps to v equals 2 for what values of u? Well, how are we going to get that? We plug in some values for x. So when x is equal to 0, this tells us that u is equal to -2. And when x is equal to 2, we get that u is equal to +2. So this is going to give us the line v is equal to 2 from from u is equal to -2, right here, -2, to u is equal to +2. Okay, so this is going to be, I'll call it S1, right? This is the transformation of R1 into our UV land. Okay, so let's erase this. Let's make some space. Let's keep going. So let's transform R2. So R2, okay, R2 under this inverse transformation here, R2 is the straight line y equals 0, and it's from x goes from 2, maybe I'll start writing it this way, 2 to 1, okay? And so what does this do to our transformation? Well, u is equal to x then, and v is equal to, well, also x, okay? And so what does this tell us? Well, this is just going to be the line u is equal to v, right? This is going to be the line u equals v for how long? Well, it's from x goes from 1 to 2, which means it's from u and v going from 1 to 2. So this bit right here tells us that, courtesy of what we have over here, that, u is going from 1 to 2, and it tells us that v is going from 1 to 2. And that's just going to be a little diagonal segment here. So from 1 to 2, like so. So that right there is going to be my S2, we'll say. Okay? And so we have our S1 going this way. Cool, great. Let's do R3. So R3, what is that? Well, I'm erasing this. Well, R3 also looks like the line y equals x, but shifted down 1. So I believe this is the line y equals x minus 1 for what values of x? Well, it's values of x from, technically from 1 to 0, so maybe I'll write it like this. From x goes from 1 to 0. And so what happens to our transformation? We just plug stuff in. So u is equal to x plus x minus 1. And v is equal to x minus 1. So this becomes u is equal to 2x minus 1. V is equal to just 1. That's super nice. So this is the equation v equals 1. And using this information right here, that's going to give us, so when x is equal to 0, this gives us that u is equal to negative 1. And when x is equal to 1, this gives us that u is equal to positive 1. So this is actually just going to give us the segment where v is equal to 1, where u goes from negative 1 to 1. Okay, so this right here is our segment S3. That's fabulous, great. The last one, by just the theory, should connect it, but because we're practicing and we're doing this, let's do R4 really quick. So R4 is the line where x is equal to 0, and this happens for the y values where y goes from negative 1, oh, I guess I'm doing this wrong. Y goes from negative 1 to negative 2, so looks like so. And so what happens with our transformation? Well, u equals y, and v is equal to negative y. And this gives us the line u is equal to negative v, right? Setting those equal to each other, but offset by a negative. And that should fit our segment. We can do the last bit of thinking, which is, what values of u and v are we going to be bounded by? But we can quickly see that it's going to give us this little last segment right here, and this is our S4. So what have we figured out right now? Here is our region of integration if we're talking about being in u and v land. Now, remember, the whole point of this, just to recap, was to execute this integral, this one right here. And we're attempting it by just saying, hey, look, if we didn't have x plus y and x minus y, we just had u and v, could we do this? Cool, great. We've done some heavy lifting in the sense that we kind of BS'd a transformation. We showed what transformation this would, what region of integration this would be in u and v. We said this would be super convenient to do in terms of u and v because this is just e to the u over v, and we could, dA, which of course is going to be either du dv or it's going to be dv du. The only thing that we're missing now is our Jacobian. Okay, the only thing we're missing is the Jacobian. I'm not going to do the bounds for u and v because I am going to imagine that you are all very well practiced at this point by coming up with the bounds, and it's actually also done in the textbook. That's not really the important part. The last important thing here is figuring out what the Jacobian is. Now, there is a way to do it looking at this thing as is, but in the way that we've been taught in the previous video and the way that the book does it, we need to get our transformation in terms of x equals and y equals. So to determine the Jacobian, right, we need the actual transformation. Remember, we were given the inverse transformation that takes us from xy to uv. We need the actual transformation from uv to xy. So to determine the Jacobian, we need, x in terms of u and v, and y in terms of u and v, right? Some function in terms of u and v. Well, let's try it. If I take this and twiddle around with it a little bit, and I rearrange the first one, I get x is equal to u minus y, right? And I still have v is equal to x minus y. What can I do with this? Let's see. I can plug in for x right here, and I get v is equal to u minus y minus another y. So what do I get? I get v is equal to u minus 2y. Now, how does this help us here? Well, I can rearrange this very nicely to get v minus u is equal to negative 2y, which in other words becomes y is equal to u minus v divided by 2, if I divide everything by this negative 2. And this right here is my y coordinate. Okay, that right there is going to be my y coordinate in terms of u and v. Well, if that's what y equals, I should be able to back substitute it into here. So I get x is equal to u minus, and then what do I get? Well, y is equal to u minus v over 2. So let's get some common denominators here and get to 2u over 2 minus u plus, how do I want to do this? I'll just keep it as a fraction like this, and now we'll simplify it. So we should get u plus v over 2 is equal to x. Great. And now from here, since we're in the 2D case, we can now use both of these to figure out the Jacobian. And the Jacobian, again, we need to take the partials with respect to u, the partials with respect to v. So for instance, dx du, in this case, is simply just going to be 1/2. dy du is going to be also 1/2. And then dx dv is going to be, wow, also 1/2. This is amazing. And dy dv is going to be negative 1/2. Okay, cool. So again, where did this come from? This is my dy, or excuse me, dx dv. This right here is my dy dv. This is dy du. This is my dx du, which again comes from those tangent vectors, right? It's the area of the parallelogram between them. That's kind of like our distortion factor. But doing this, we get negative 1/4 minus 1/4, which is non-zero. This is equal to negative 1/2. Cool, great, fabulous. So, what, great. What do we do now? Well, at this point, we have everything that we need, right? We have the Jacobian. We have, did I make a mistake here? Let me see. I was like, this shouldn't be negative. Let me see. X is equal to u minus 1, u plus v, dx du, dy dv. Don't think so. Yeah, I think we're good to go. So anyways, the whole point here is that now we have everything that we need. We have basically, using a change of variables, come up with a Jacobian. We've come up with an e term that we can actually integrate. Our Jacobian ends up just being a number, which is the best thing completely possible. And we can come up with the bounds of our region in u and v, no problem. Remember, and all of this to just circumvent the fact that we couldn't even integrate this to start. Right? That was the whole point. So anyways, this is kind of like the hardest example you might be given, right? And the process is here. So this is different from the last one because instead of me giving you a region in terms of u and v and being like, what does it look like in terms of x and y, and then doing an integral, this was like, hey, what if I give you the region in x and y? Can we come up with a transformation and use it in a constructive way to solve an integral, which we absolutely can. So that's going to do it for, change of variables. And this came at the tail end of a triple integral section. Everything that we've learned works for triple integrals. Remember that the cross product, the determinant of a cross product or the magnitude of the cross product is obviously going to involve a 3×3 determinant if we have to do change of variables for 3 variables instead of 2. But again, also in the textbook, no problems. So hopefully the intuition makes sense. Hopefully the process makes sense. Hopefully I didn't make any mathematical mistakes. And hope you guys are enjoying so far. Next week we get to hop into vector fields and line integrals, and this class kicks it into high gear. So I hope that you are ready. Enjoy the rest of your week, guys.